we're going to be considering the limit as x goes to 0 from the positive side, so from the right side, of the function x times natural log of x. And we're going to use this example as a way to demonstrate how we can utilize L'Hopital's rule, but then how we've got some decisions to make to be able to adjust our indeterminate form into one that's appropriate for L'Hopital's rule. So first notice that if we try to figure out what this indeterminate form is, the first thing we try to do is just plug in. And so really what we're looking at here is like a 0 plus times the natural log of 0 plus. Well, we need to be able to interpret what the natural log of 0 plus is. And so to do that, we rely on the graph of what the natural log of x looks like. So this is natural log of x. And so when we're looking at 0 plus, we're saying as x is approaching 0 from the positive side, so from the right side, so we're looking at that arrow. And so this function here then is approaching negative infinity. And so we do see then that this is really a 0 times negative infinity indeterminate form. A 0 times negative infinity indeterminate form is not one of the ones that's appropriate for L'Hopital's rule. To be able to apply L'Hopital's rule, we either need a ratio of zeros or a ratio of infinities where it doesn't really matter what the sign with infinity is. And so here, anytime we have a 0 times an infinity or negative infinity, we've got options. We could either shoot for 0 over 0, or we could shoot for one of the infinities over one of the infinities. And the reason that we can do that is because 0 and the infinities are in some sense reciprocals of each other. So we're looking at something that's 0 multiplied by something that's infinite. So our first attempt here is going to be shooting for a 0 over 0. So what we need to do is we need to flip the term that was going to the negative infinity and stick it in the bottom. So if we both flip and stick it in the bottom, then it's like dividing by, or multiplying by the reciprocal, dividing by the reciprocal. We're doing two inverse operations there. Natural log of x on the top, if you push it down to the bottom, needs to be 1 over natural log of x. Okay? And so that took the term natural log of x that was going off to negative infinity, and it flipped it and put it in the bottom. And so now when we plug in and we see what we're looking at here, we've got the 0 plus on top, but then again we've got the 1 over natural log of 0 plus in the bottom. So that would then be like a 0 plus on the top and a 1 over negative infinity on the bottom. But then the reciprocal of plus and minus infinity there is going to be 0 on the bottom. So we're really looking at a 0 over 0 indeterminate form. And a 0 over 0 indeterminate form means we can apply L'Hopital's rule. And so to apply L'Hopital's rule, what we do is, and sometimes we write the LH or H on top of the equal sign to indicate that's what we're using here. What we do is we take the exact same ratio, but this time the derivatives of it. So we're looking at the derivatives, there's your d dx, of the top was x, and then the bottom is the 1 over natural log of x. And so we need to take the derivative of each one of these. The derivative of the top there is the derivative of x, which is just 1. And the derivative of the bottom, we could use a quotient rule, or we could think about this 1 over natural log of x as natural log of x to the negative 1 and use like a power rule, chain rule thing. Either way you do it, you end up with negative 1 over, well, hang on just a second. Let's just go through the quotient rule. That way I'll show you the whole details there. So the quotient rule, we take the bottom and it's natural log of x there and we square it. So when we're talking about the quotient rule, we have the derivative of the top, which is 0, times the bottom, which is natural log of x, minus the top, which is 1, times the derivative of the bottom, which is 1 over x. Okay? So you see how these problems can quickly become fairly involved because you've got to keep track of what derivatives you're taking. So now, at this point, let's take a step back here and do some algebra. We've got the limit as x goes to 0 from the positive side, and we've got the 1 here on top, but then if we clean up the bottom here, we end up with like a a 1 over the x times natural log of x quantity squared, because see this x here that is at the denominator on the top of that quotient rule part gets pushed down to the bottom to be with the natural log of x factor that's squared. And so we're really looking at then limit as x goes to 0 from the positive side. If we're dividing by that fraction, we multiply by the reciprocal, so we're looking at x times natural log of x, this time squared. So now, sometimes when we're looking at L'Hopital rule problems, we have to apply L'Hopital's rule more than once, or we apply it once and then we have to do some algebra before we reassess how to take the limit. So when we're looking at this, really as clean as it can be, and we're ready to tackle the limit one more time, before running in and going through all these steps again, take a look at this x times natural log of x squared compared to what we started with. It's more complicated. And so in some sense, we haven't made progress, we've made it worse. And so remember here, we made a choice at the beginning. We decided to take the term that was going off to negative infinity, flip it and put it in the bottom so that we would have a 0 over 0 indeterminate. But perhaps that wasn't the best approach. So let's try the other approach. Rather than shooting for 0 over 0, let's try for shooting for infinity over infinity, where the sign of the infinity doesn't really matter. So this is the exact same problem we're looking at. This is just the second attempt here. We already assessed that the indeterminate form was 0 times negative infinity, but this time we are going to flip the other term. The one that was 0, we're going to flip it and put it in the bottom. So x was going to 0, so we're going to take that x and we're going to flip it, take its reciprocal, and put it in the bottom. So that's kind of flipping it twice, really. And then we have the leftover natural log of x on the top there. And so you do see then that as we take this limit, we're looking at natural log of 0 plus over 1 over 0 plus. And we know that the natural log of 0 plus, we already looked at that graphically, that goes to negative infinity. And then 1 over 0 plus, that would be shooting up to positive infinity, because dividing by 0 would be multiplying by infinity, and since that 0 has the plus sign attached to it, it would be positive infinity. But this is also, this ratio of infinities is one where we can use L'Hopital's rule. So that's what we're going to do. So we've got the L'Hopital's rule being applied here. So we've got the limit as x goes to 0 plus. Now instead of the ratio of the functions, we've got the ratio of the derivatives. Notice this is not a quotient rule. It's the ratio of the functions goes to looking at the ratio of the derivatives of the functions when we are looking at the limit with an appropriate indeterminate form. So now we are ready to take these derivatives. The derivative of natural log of x is 1 over x. And the derivative of 1 over x, I'm really going to, in my mind, this one we can do, I think, just without rewriting, but perhaps just think about it in our mind. 1 over x is x to the negative 1. So if I'm thinking about x to the negative 1, that derivative would be negative x to the negative 2. So it would be negative x, or negative 1 over x squared if I push that back so that I don't have negative exponents there. If you need to do some side work or show some extra details, go for it. You definitely don't want to miss these derivatives. But with practice, I think a lot of these derivatives you've done several times and you can probably handle. All right, so at this point, after you've applied L'Hopital's rule, always I recommend doing algebra to do any sort of simplification that you can before you reassess your situation. This is like what we talked about when we're doing limits back before we had the use of L'Hopital's rule. Whenever you try to limit and then you did something algebraically, you always go back and simplify before you reassess. And so here we're looking at the limit as x goes to 0. We've got the 1 over x, and then we'd have times the reciprocal of that negative 1 over x squared. So that would be like the x squared over negative 1. And so notice we've got a copy of x that cancels here. So we've got limit as x goes to 0 from the positive side, and so we would just have the negative x. And guys, that limit I know you can do. You can do it simply by plugging it in. And so we've got, when we plug it in, we've got a negative 0 plus, which is really just a limit of 0. And so we see that after one application of L'Hopital's rule with a little bit of algebra, we can get the answer here completely done. And so then notice that the first try that we attempted, we were kind of just guessing which one should we shoot for, which one should we flip and put in the bottom. And we saw that it didn't help us when we had to take the natural log and flip it in the bottom. That derivative was too complicated, not enough things canceled, and it just made things worse. But in comparison, by keeping natural log up on the top where it was, notice that the derivative of natural log of x is just the 1 over x. So in some sense, we make progress by leaving the natural log of x alone, even though flipping the x and moving it down to the bottom as 1 over x made that derivative more complicated. In the end, we had the x's that were canceling to help us out. And so really the take-home message at looking at this and trying to determine which direction should you go, often you're going to want to just leave the more complicated type functions alone on the top, because it starts making them worse when you flip it and put it in the bottom and need a more complicated derivative in the end. So kind of a rule of thumb is more complicated functions just leave alone, and powers of x in general, those aren't as obnoxious to deal with. That might be one that you want to just kind of flip and put in the bottom and see what you can do. But it just takes some practice and some experience to see what really works out.